So hello everyone, welcome to our topic. This is Chenmin and Yipeng Hongjun online, and today our topic is handling the elephant flow on a DPDK-based load balancer. So here's the agenda. Oh, sorry, I forgot to present. So here's the agenda. As our work is based on the HDSLB product, so first let's have a quick review of the HDSLB so that you can understand the background clearly. And the next is the problem, how to handle the elephant flow. And then Yipeng will introduce the innovative algorithm to detect the elephant flow. And then I will introduce the Intel new hardware accelerator DLB and our whole solution. Okay, and at last it is the key takeaway and the acknowledgement. Okay, let's start. Okay, our work is based on the HDSLB product. HDSLB is short for the high density scalable load balancer, and it is based on the DPDK. It is a DPDK-based layer 4 load balancer, and we have achieved the industry challenges on this product. Here are some. Here are some highlights. The HDSLB is fully optimized with Intel processor and NIC, and it is able to handle 100 million concurrent connections, and it can handle up to 150 million PPS level throughput. And what's more, it is able to handle 10 million PPS level elephant flow. And the last one is our today's topic. So everybody here should be very familiar with this DPDK run to completion model. The load balancer itself processes the flows using the multi-worker core corresponding to a queue. And use the RSS2 source. However, flow are not equally. It is reported that 10% of the flows, we call it the elephant flows, may take 90% of the bandwidth. So a small number of the elephant flows may not be balanced by the RSS. So in this figure, we can see that the worker core 3, I have marked it in the yellow, is overloaded, and life is too hard for him. When he's fighting with the elephant, is my immediate fire. So why we need to treat the elephant flow and the mice flow separately? There are two reasons, I think. The first one is that the huge volume of the traffic from an elephant flow could exceed one core's processing capability. And besides, the elephant flow and the mice flows could impact each other. If the elephant flow starts dropping, it will start the congestion avoidance, like retransmit, resize the congestion window, and so on. You can imagine what will happen if an elephant flow tripped over a mouse. So that's the reason why the elephant flow needs special treatment. And our proposals are: step 1, we need an efficient heavy hitter detection algorithm. Then we should distribute the elephant flow to multiple cores for parallel processing. And at last, we order the parallel flow among the cores. Maybe these 3 steps makes you remember a famous Chinese joke: how to put an elephant into a refrigerator. So just kidding. Let's see our solution. Here are some key components. The first one is the heavy hitter detection algorithm. It is based on the state-of-the-art heavy hitter flow detection algorithm Natural Sketch, and it is implemented and optimized for the Intel platform. So in the next page, Yipeng will share the details. And the next is Intel DLB. We use this accelerator to distribute the elephant flow among the multiple cores. And at last, I will introduce the whole processing pipeline. Okay, so welcome Yipeng to introduce our heavy hitter detection algorithm.
Also, thanks Hongjun and Chenmin leading the projects, right? I guess I will just give a couple of words on the algorithm itself briefly. So basically, a heavy hitter detection algorithm's responsibility is to profile the packets as they flow through the application and bookkeeping necessary information to detect the heavy hitters or the elephant flows. And every while, the controller may query using the algorithm to query the heavy hitters. What are the heavy flows you have seen from this algorithm? So that's basically what the algorithm is doing. And the algorithm itself, we put into the load balancer, is based on the Nitro Sketch, which is a state-of-the-art algorithm we find in academia. It was originally proposed by Professor Liu in SIGCOMM conference, and basically the algorithm itself consists of a couple of internal data structures: a 2D counter array, a hash table to indexing to a min heap, the min heap itself to bookkeep all the full keys of each heavy flow. So every time a packet comes into the algorithm, it first updates a counter array, and for every potential elephant flow, it will go to the check the hash table first, and to check if it's in the min heap. If it's there, then it will update the counter in the min heap as well. If not, then we insert the elephant flow into the min heap. Right. So, and every while when you feel necessary, just the controller will send a query to the algorithm, ask about like what are the heavy flows, what are the elephant flows, give me all the information of them. The algorithm itself is a sampling based. That's great because we can tune the sampling rate up and down depending on how much throughput you need, how much cost you can tolerate. So, for example, we use 1% yearly, which already meet our requirement, which means like we only sample 1% of the total packets to kind of accurately get all those heavy hitters. We also use the hash table here to speed up the lookup time into the min heap. So currently we are collaborating with the professor from Boston University, the author of Natural Sketch, to further improve the algorithm. It's just a brief description. For more details, you can look into the paper. Just Google Natural Sketch. It's a very nice algorithm. Yeah. Okay, that's it, I guess, for the algorithm. Please continue, Chenmin, for the next. Thank you.
Oh, okay. Thanks, Yipeng. So for this algorithm, from our user's perspective, we just feed the packets into your algorithm, and then you could report which flow is the heaviest flow, right? Okay. So thanks, Yipeng.
Thanks.
Very good algorithm. So now, okay. So now we are able to identify the elephant flow. Okay. Then the next step is to handle it. In our solution, we use the DLB for the distribution as well as the reordering. So DLB is a hardware accelerator available in Intel's latest processor. It is short for the dynamic load balancer. And it exposes as a PCIe device and acts as an event dive in the DPDK. You could find its code in the DPDK 20.11. It has already upstreamed. Okay, it supports a variety of working modes, and the red figure is what we used today. In this mode, the producer could enqueue the packets into the DLB for the distribution and order tracking, and the worker here could dequeue the packets from the DLB, then do the parallel processing among these workers. Okay, and after that, the worker will enqueue the packets to the DLB again for the reordering. So this is the character of this mode. The packet will pass through the DLB twice. Okay, in the next few pages, I will introduce the whole picture of our solution. But before handling the elephant flow, let's see how does the HDSLB handles the mice flow. Sorry. Just like all the DPDK-based applications, there's one main core and several worker cores. Each worker core is bounded to a queue. When a flow comes from the network, the NIC will steer them to one of the queues by the RSS, and the worker will receive the packet through the PMD. In this figure, core worker 0 got it and start processing. First, it will look up the connection table, find out the flows information like which root server does this flow belongs to, and how to do the I mean the network address translation. This is a key workload in the load balancer. So as these workloads are not very important to today's topic, so I compressed them as other workload to make this figure simpler. At last, the worker transmits the flow out of the network. Okay, so this is how does the HDSLB handles the mass flow, and let's see how to enhance it to handle the mass flow, the elephant flow. Let's see how to handle the elephant flow. So the first step is to detect the elephant flow. I deployed the heavy hitter detection algorithm here on all the worker cores pipeline, and this algorithm will then monitor all the flows and find out the heaviest flows among them. Then I deployed a heavy hitter control center on the main core here. It will periodically fetch the heavy hitter reports from all the workers, and find out which one of them is heavy hitters is the elephant flow. You know, there should be some criteria of elephant flow, like the flow established time, the bandwidth, and so on. So you can have your own criteria. So after finding out the elephant flow, the heavy hitter control center will then clone the elephant flow's connection table information to all the workers so that all the workers can handle it. And at last, it will program RTE flow to the ingress NIC to redirect the elephant flow to a dedicated core. You will soon see how does it work in the next page. So we have programmed RTE flow in the ingress NIC. So when the elephant flow comes, it will redirect by the RTE flow in our NIC. It is a switch filter. It will be redirected by this switch filter to the standby producer core. Okay, this standby producer doesn't do anything but including the elephant flow into the DLB here for the load balancer and the parallel processing among the workers. Then each of the workers dequeues the partial traffic and process it just like the mice flows, look up the connection table and do other workloads. But it won't directly transmit the packets out of the network. Instead, it will enqueue the flows into the DLB again for the reordering. And at last, the consumer core dequeue the ordered packets from the DLB and then transmit them out of the network. Okay. One thing I want to highlight here is that doesn't like the normal run-to completion model. This is a pipeline model. You can see the packet flows from one core to another and to the consumer. So in this model, you must be very careful to insert the prefetch and the cell demote instruction in your code to handle the catch misses. Otherwise, the whole pipeline will waste a large number of CPU cycles on waiting the catch sync up among the cores. Okay, if we review the whole solution again, we can say first I leveraged the Nix RT flow capability to redirect the elephant flow to a standby core. This helps us eliminate bottlenecks on the producer. And as the packet and buffer will be transmitted from one core to another, you say it is allocated from the producer core and then processed on the worker core, and then at last released on the consumer core. So we created a dedicated packet and buffer pool for this pipeline to avoid the side effects to the normal worker cores. And we also leveraged the DLB for the load balancing and the packet reordering. They saved lots of CPU cycles. In fact, we also implemented a pure software solution, but the performance is not as good as the DLB version. So here's the perf comparison. The orange one is the original perf, and the green one is the DLB solution perf. You can see that there is a very huge improvement when the packet length is less than 512, and if you compare the performance of this 96 packet length, you can see there is it's almost 3 times of the original perf. If you compare the DLB solution with the software solution, I marked it in the yellow. You can see there is also a very big improvement. And what's more, the software solution is not as stable as the DLB solution, and sometimes you can see there is some perf drop like this here. So here are some key takeaways. First, distributing the elephant flow to multiple cores is essential. We have explained the reason the elephant flow would exceed a single core's capability. And we improved the state-of-the-art elephant flow detection algorithm, and we leveraged the Intel's new load balancer accelerator DLB to reduce the overhead. And we use a dedicated packet and buffer pool in the pipeline to avoid the side effects to the other workers. And we use the prefetch and the cell demote instructions to handle the catch misses. And we also leverage the Intel NIC's offloading capability to accelerate the packet processing. I hope this could help you in the work. Okay, so at last, I would like to take this opportunity to say to thank the powerful team behind us. Thanks Jay, Han, Maritika, Rahul, Niall, Pravin, Samay, Ren, Charlie, and Professor Liu at Boston University. Thank you all for your contribution and support. Okay, thanks for listening, and it's Q&A time. If you have any questions, please feel free to post them in the chat window. Thank you. Okay, let's see. Is there any questions? Okay, here we got a question. May the standby producer and the consumer be a bottleneck? Oh, in fact, we did a lot of tests, and finally we found the standby producer core won't be the bottleneck. Okay, this question is from Emily. Is the elephant flow easy to appear in the network? Yes, it is very it's very easy to appear in the data center network. If you look into our brief introduction in the DPDK Summit website, there I put a link there. You could find that there is almost 10% of the flows are the elephant flows. And I also mentioned that the 10% flow elephant flow may take around 90% of the bandwidth. Okay. So does going through heavy hitter and DLB add latency, or do you have much latency or had? Yeah, of course. This solution will bring the additional latency, but as I just said in the slides, it is very important to handle the elephant flow. Otherwise, it will impact other mice flows. So we don't have other choice but to handle it. I know one of
a quick comment. So the heavy detection algorithm itself is sampling based. So we only sample like 1% of total packets. That's first. Second is like even on average, I think we measure about tens of cycles added. But that's a good question. Like we probably can do more evaluation and look into the latency for the particular packet that we sampled. But I don't think it's a big concern, like considering the whole end-to-end networking, also the processing time of the load balancer itself, and also the business logic like in the backend server. So it won't add that much. Yeah, that's a comment. Yeah, please go ahead, Chenmin.
Okay, thanks, Yipeng. Thanks for explanation. And the next one is why bigger packet have less impact? No. In fact, when the packet length is larger than 2056, it has already reached the line rate. So there is no gain on the DLB solution. What is the PPS number at performance growth? Sorry, I can't publish the the number, there is some legal problems. But you can see the ratio when the packet is not very long, there is more than 3 times performance gain. All right, let's wait 1 minute to see if there are any more questions. Okay, if there's no, okay, so thanks for your listening. Thank you. That's all.